This is Flowline Chronicles, stories of water, people, and the future we share. In the previous episode, we spoke about why long-term planning assumptions often struggle in a world of growing uncertainty. But planning does not fail only on paper. It fails inside machines, inside pipes, and inside power bills. In this episode, I want to look at what really happens when water systems are pushed beyond their intended operating range, and how those technical stresses quietly turn into energy losses, maintenance problems, and budget pressure. This is not about blaming designs or operations. It is about understanding the chain of cause and effect inside real systems. Most pumping systems are designed around a best efficiency point, a range where the machine is stable, efficient, and mechanically comfortable. But in reality, systems rarely stay there. As demands change, or as constraints appear elsewhere in the network, pumps are often driven towards higher flows or unfavorable operating zones, sometimes even into runout conditions. At first glance, this may look like better performance. More flow seems like more delivery, but hydraulically and mechanically, this is where stress begins to build. Efficiency drops, hydraulic stability reduces, and the machine starts working harder, not smarter. When pumps operate away from their ideal range, the risk of cavitation increases. Cavitation is not just a noise or a vibration problem. It is a material and mechanical problem. Tiny vapor bubbles form and collapse, attacking the impeller surfaces. Over time, this erosion changes hydraulic profiles, increases imbalance, and introduces vibration. That vibration does not stay in one place. It increases the load on bearings. It stresses seals and couplings, and it slowly shortens the life of the entire rotating assembly. Very often, none of this causes immediate failure. The system keeps running, but it is quietly aging faster than planned. One of the earliest signs of this hidden stress is almost always energy. As hydraulic conditions worsen and mechanical losses increase, the power drawn by the system rises, often disproportionately to the useful output. In simple terms, the system starts consuming more kilowatts for the same cubic meters of water. This is why energy bills often reveal distress in a system long before a major breakdown occurs. Energy is not just a cost. It is a diagnostic signal of how healthy or unhealthy a system really is. There is another multiplier in this story: material selection. Different applications demand different metallurgy, depending on water quality, solids, chemistry, velocity, and cavitation risk. Choosing minimum grade materials may reduce initial capital cost, but under off-design operation, cavitation and vibration attack weaker materials much faster. Impellers lose profile, clearances open up, efficiency drops further, and the cycle of higher power, higher maintenance, and shorter life accelerates. Better metallurgy does not just improve durability, it helps preserve hydraulic performance and mechanical stability over time. So material choice is not only a purchase decision, it is a life cycle performance decision. All of this eventually shows up where every project feels it most, in the budget. More frequent bearing and seal replacements, shorter overhaul cycles, higher energy consumption, reduced asset life compared to projections. What looked like a temporary operational compromise slowly becomes a permanent financial leak. This is how technical drift turns into OPEX overruns, distorted life cycle costs, and assets that underperform their original promise. Not because the system was badly intended, but because it was forced to live outside the conditions it was designed for. There is a deeper lesson in all of this. In water supply and infrastructure projects, mechanical and hydraulic design must lead based on real site conditions, real operating ranges, and real life cycle expectations. Civil structures should then be designed to support those mechanical realities, not constrain them. International design standards are built around this sequence for a reason. Define the system hydraulically and mechanically. Define the operating envelope. Define material and performance requirements, and then shape the civil works around those needs. When this sequence is reversed, systems are often forced into compromise from the very first day of operation. Runout operation, cavitation, vibration, energy loss, material degradation, and budget stress are not isolated problems. They are different expressions of the same system imbalance. If we want reliable, efficient, and long-lasting water infrastructure, we must start by respecting how machines, hydraulics, and materials actually behave, not just how drawings assume they will. Because in the end, good infrastructure performance is not achieved by hope or habit. It is achieved by designing for reality. Flowline Chronicles, where every story reminds us of the delicate balance that keeps us alive